been looking at linear relationships between variables and how economists think about these. So far, everything that we've looked at has had a constant slope. That is, we've been analyzing straight line relationships, such as the relationship between price and quantity in Bob's demand for hamburgers. Now we're going to look at a relationship that is not linear. In fact, it's what we call curvilinear. It is a line that's not straight. We're going to see how we draw a relationship like that and how we calculate the slope of a relationship where the slope is not constant. In order to do that, let's look at the relationship between labor and output for a firm that makes television sets. And I've made up these numbers so that I can fit a curvilinear line to them. Here is my relationship. If you have one worker working by himself, he can make a single television in a day. If you have two workers cooperating, they can make 4 televisions in a day. If you have 3 workers, 9, 4 workers, 16, 5 workers can make 25 televisions, and so forth. Now, notice this relationship is one of exponential increase. That is, the number of TVs are increasing much faster than the number of workers. So in this case, our slope will not be constant. Let's represent this relationship now in a picture. I'm going to take my axes here and use the axes to represent the amount of labor that the firm uses. So we're going to measure labor on the horizontal axis. And on the vertical axis, we're going to measure output. And in this case, it's going to be output of television sets. So each point in this space will represent a combination of labor and output. This is a production relationship. So, for example, one worker is able to produce a single television if he's working by himself. So since I've calibrated these axes where each of my lines represents 2 TVs, my first dot will be halfway up towards this point at 1 worker and 1 television set. So here's my first point on my product curve. The second point on my product curve will be 2 workers and 4 television sets. So that's going to be at this point right here. 3 workers are able to produce 9 television sets, so that gives me a point like this. 4 workers are able to produce 16 television sets, so follow this line up here to 16. And 5 workers can produce 25 television sets, so follow this line all the way up to 25, which will be right here. Now, connecting these dots is going to be a little bit more complicated than connecting the dots in our earlier story. In the earlier story, all we had to do was pick any 2 points, draw a straight line between them, and we had a demand curve. But the production curve is not linear. That is, the slope is not constant, so I have to draw a curve that connects these points together. That curve is going to look something like this. Let me take a curve here and figure out how to make it fit. I want it to go through this point, and this point, and this point, and this point, and this point. And so my curve is going to look something like this. It's going to be an exponential relationship. So if I want to connect my dots, I'm going to have them lying along a blue line that looks like this. Let me go ahead and draw that blue line in. I could have kept that curve there and just drawn along it, but I'm going to try, and it takes practice to do this well, to connect my blue dots along a single curved line. It's like this. Well, that's not bad. So I'll go ahead and make this line a little bit darker. And there's my production function for a firm that hires workers to produce television sets. And we might call this curve the total product curve. We'll be studying this later in the lectures. So I'll go ahead and label this TP, total product. And this total product curve depends on lots of things, like the technology of the firm and the size of their factory and other things. What I'm mainly interested in at this point, though, is figuring out what the slope of this curve is at a particular point. Say, for instance, we are looking at this point right here, the point where we're hiring 2 workers and making 4 television sets in a day. And I'd like to know, what is the slope of the curve at this point when I'm hiring 2 workers and making 4 television sets a day? What's the slope of the curve? That is, what's the rise over the run? How many extra television sets will I be able to produce if I hire an extra worker? Well, to calculate the slope of a straight line, it's not quite as simple as looking at 2 points on the curve. Because as you move from one point to another, what's happening is that the line itself is changing its slope. Down here, our blue curve is relatively flat. That is, if we look at a point down here, we get a relatively flat line. But as we move up the curve, notice the line is getting steeper and steeper and steeper. The slope is changing all along this blue curve. So if we want to calculate the slope at a particular point, we can't just look at the slope between 2 points on the curve, because as you move from here to here, even that small movement represents a change in the slope, or causes a change in the slope of my total product curve. The blue curve slope is changing. Well, here's how we do this. We calculate the slope of a single point on this curve. We calculate the slope at a single point by taking the limit of slopes of lines that connect 2 points on the curve. So for instance, suppose we look at what happens as we move from 2 workers to 4 workers. As we move from 2 workers to 4 workers, what happens is this. We're moving along a line that connects those 2 points. And the line that connects those 2 points is this line right here. This red line connects those 2 points. Now, what's the slope of that red line that connects this dot with this dot? What's the slope of that line? Well, let's calculate it. The slope of my red line here is equal to the rise over the run, or the change in the vertical axis variable, that is a change in the number of television sets, divided by the change in the number of workers. Well, the change in the number of television sets is going to be 16 minus 4, which is going to be equal to 12, and divide that by the change in the number of workers, which is going to be 4 minus 2, and that's going to give me a slope of 12 over 2 equals 6. The slope of this red line right here, that is its rise over its run, is going to be 6. The slope of that line is 6. However, if I took a different red line, say the red line that connects this dot to this one, its nearest neighbor, we're going to get a different slope. Let me go ahead and draw that. If I connect this dot with the nearest neighbor, my red line is going to be a bit flatter. Now, it's a little harder to see that line because it's almost right on top of the blue line. But what we've got here is a line that connects this dot with its nearest neighbor. I'd like to know what's its slope, what's the rise over the run as I move from this point to the next. So let's look then at the slope as we move from 2 workers to 3 workers. In that case, the slope once again is rise over the run, but the slope along this point is going to be a little bit different. The slope in that case is going to be equal to, the output has changed from 9, or to 9 from 4, divided by a change in workers from 2 to 3, gives a slope of 9 minus 4 is 5 over 1, which is going to be equal to 5. So the slope at this point is 5. Notice what's happening. As we move from this original red line that connected these 2 points to the red line that connects 2 closer points, the slope is getting flatter. It's gone from rise over run of 6 to rise over run of 5. Eventually what happens is if we let the point that we're looking at get closer and closer to our original point, if we let the point that we're looking at get closer and closer to our original point, we're eventually going to come up with a line that has a slope that is equal to the slope of the blue curve itself. Eventually what we get is what we call a tangent line. The tangent line is the line that just touches the blue curve. If you had something straight like this ruler and you wanted to lay it against the blue curve, laying the ruler against the blue curve would give you the tangent line. Laying something straight against a curved line at a particular point gives you the tangent. Tangent means touching. If you wanted to take the blue curve like before and lay it against the blue curve and have this blue curve be a straight line, the slope of this blue curve now is the slope of the tangent line, the line that just touches. So to calculate the slope of a curve at a particular point, you take the limit of the slope of the lines that connect that point to other points, and that limit is going to be the tangent line, the slope that's tangent. So when we're looking for the slope of a curved line, we take the slopes of lines that connect points on the curve, let those slopes change as the point gets closer and closer to the point we're interested in, and finally we come up with a line that's tangent to the curve at the point we care about. In this particular case, from calculus, I know that the tangent line that I've drawn here with a dash has a slope of 4. I'm not going to do the calculus right now, but what I'm interested in your understanding is that when you have a curved line, the slope of that line changes as you move along it. And the important thing for you to know that the slope of that curve at a particular point is the slope of a straight line that touches the curve at that point.